All right, so we're going to review steering and focusing today and what phasing has to do with those two concepts. So steering and focusing both can be done either mechanically or electronically. And so we're going to start by looking at how they are done mechanically. So if you had mechanical steering of a transducer like they all used to be back in the day, you would actually have a motor component inside of the transducer, and in order to bend this beam, it would have to move the actual elements. So typically if there was no movement of the motor, right, your beams would come down straight, and this motor could actually tilt your beams or tilt your elements, and then it could send signals out. So to mechanically steer, you would actually physically move the elements side to side. For mechanical focusing, they would take a lens, either internal or external, and they would put it on the transducer in order to focus the beam. So if you can imagine, right, that typically these beams are going to come straight down out of the elements, and if we added a curved lens, a convex lens here, what happens is that the beam comes and then bends and winds up focusing, and we wind up with this focal part, this more narrow part of the sound beam. So you could mechanically steer and mechanically focus a ultrasound transducer. These days our transducers are doing these same things but electronically. So electronic steering is done through a process called phasing, right? So that's where the phasing comes in. And all phasing means is that it is a delay in sending signals to certain elements. We do it in phases to get the desired result that we want. So if you did not have phasing on this ultrasound beam and you sent the electrical signal at the exact same time to each of these, so the same timed pulse, what would happen is that your beams would go straight down all together, okay? But what we do instead is that we delay the sending of the beams, or the sending of the pulses, so that each element activates slightly different timing, and that delay causes the beam to bend because of Huygens principle of wavelets interacting. So if we zapped this element, then this one, then that one, then that one, then that one. So this is representative of the time delay, right? And so what would happen is that this one would go first, then this one, then that one, then that one, then that one. And because of the way that they were delayed, the wave front will actually come out and bend in the same direction of the delay, right? So if we were to delay these in the opposite direction and zap over here first, and then here, and then here, and then here, and then here, our wave front would go in that direction out of the transducer. So focusing is done electronically also with phasing. So again, just with timing delays of our electrical signals. So in order to focus a beam, we need to zap in a curved pattern. So typically if there's no electronic focusing of a beam, the way that the beam interacts, there is a natural hourglass shape to it, where it will get a little bit narrower in the middle here and then diverge again in the far field. But when we use a curved pattern, which means we're gonna send our electrical signal on the outside, inner, all the way to our middle, and we have this curved pattern of sending our electrical signals, what happens is these go first, then these, then this one, and actually because of the way that they interact, they wind up creating a much narrower focus, and that is our focusing of our beam electronically. So now these can be combined, right? We can electronically steer and electronically focus at the same time with phasing. And what that might look like is that we will delay our timing on an angle, but also in a curved pattern. So we would do here and then here and then here, and then here, and then here, and we still get a curved pattern but on a slight angle. And when we do that, we wind up with a beam that both focuses and steers at the same time by using phasing. Now let's talk about this in terms of our actual transducers. So the most common one that we think about with phasing is the phased array transducer. This used to be the only one that had phasing, right? But now we do have phasing on some of our sequential transducers as well. So this phased array transducer has a rectangular footprint, and the elements are lined up right along the footprint. But this phased array transducer makes either a vector or a sector shape image. So this is a vector shape here. A sector would come out of a common point of origin and look more like that. And so in order to do that, it has to steer to the outside portions. Otherwise, it won't be able to get scan lines out here. So you can imagine with this rectangular shape, right? If beams came straight down, we would be able to gather information from this spot here. But how are we getting the information from out here? And we're doing that by phasing. So what we're doing is this transducer is zapping all of these elements, right, in a way that sends a beam this direction, and then zapping in slightly different pattern to get a beam to go this way, zapping in slightly different time delay to get a beam to go that way, then probably zapping all together to get some straight scan lines, and then it would change how it was sending, and the time delay would go this way, and we would have scan line information coming this way by steering in that direction. Now, traditionally, our linear sequential transducer could not steer, right? Unless it had a motor that was doing it, it would just send sound beams straight down. It has a rectangular footprint, so it makes a rectangular image. Now, typically today, that's how we still use it. But as you saw in lab, right, we can bend that whole image if we want to, or we also can make this into a trapezoidal image. And when we make it into a trapezoidal image, we need that same sort of phasing process. Now, traditionally what happens with a linear sequential is that each element is actually a small group of elements, right? And it will zap in order. So it would zap here to get scan line here, zap, scan line here, zap, scan line here, zap, scan line here, zap, scan line here. And that's mainly what this still does. But when it gets to the edges, it has to do a little bit of phasing. So most of our information is still gathered just by going in sequence, but we also do a time delay kind of on each side of our groups so that we get the information that's out here in the wings. Your curved sequenced array isn't usually going to be able to steer, although some modern ones might be able to. It gets this side information because of its physical shape. It has that convex footprint, which means that its elements are kind of already in a curved pattern. So this goes in sequence where each one of these elements is actually a subgroup, and it's going to go this one first to get this scan line, this one here to get that scan line, then here, middle, here, there, here, there. Because it's physically already shaped that way, it can send scan lines straight out without steering in order to get the information on our edges.